So last lecture we talked about how to speed up the Johnson-Strauss lemma by making the matrix pi, the embedding matrix sparse. That's actually the second way people thought to speed up JL, or the second way people got asymptotic improvements to embedding speed up. The original way was actually something called the fast Johnson-Strauss transform. That was originally introduced and analyzed by Eilon and Chazelle in a paper in 2006. So today I'm going to tell you about their FJLT, the fast Johnson-Strauss transform, and I'm going to show you the original analysis. And many years after that, there was another paper by Kramer and Ward who gave just a totally different way of thinking about why constructions like the FJLT works, and it gives different bounds. So I'm going to show you that as well. And they use ideas from an area called compressed sensing. You've seen a little bit of compressed sensing and that it's related to the heavy hitters problem. But we're going to talk more about compressed sensing later in the semester. Okay. And again, just a reminder, PSET 1 is due Friday, the day after tomorrow. And I moved my office hours. I hope you all got the email. I moved it from Friday to tomorrow so that people have more than 12 hours to digest what they heard in office hours and go back and work on their PSET. And another thing to keep in mind also is the project proposal. So that is due soon in a couple, I don't remember the exact date. Is it October 28th? It's on the website on the syllabus. So just take a look at that. Actually, there's a project page on the website. So take a look at that for the, what's expected of you. And if you have questions before you submit your proposal, come to office hours, talk to me about it. Or if you can't make office hours, send me an email and we can schedule another time. Okay, great. So let's get to it and let's start talking about the fast Johnson-Strauss transform. So before, on Monday, we talked about making pi sparse, right? So remember, for us, with linear embeddings, we've been looking at embeddings where, some vector z gets mapped to pi z. And Monday, we made pi sparse. Right, and if it's very sparse, then you get faster embedding time. Today I said we're going to look at the FJLT, and the basic idea is to use sampling. What do I mean by that? Take a matrix S, which looks as follows. It has D columns where D is the dimension of the original vector and it's mapping down to M rows. And if you look at each row, it just has a 1 in a random location and the rest of the row is 0. And every row is like that, independently. Okay. So, what is S times Z? S times Z is just taking, IID uniform samples from the vector Z and putting those samples in a new vector, which is SZ. Okay. Now, if you look at any, one of the entries, like if you look at SZ, SZR, look at the rth entry of SZ, and ask yourself, what is the expectation of the square of that? That's equal to, right, the sum I goes from 1 to D, the probability that we sample I times ZI squared. And if we're doing uniform sampling, then the probability that we sample I is 1 over D, right? So this is equal to this is equal to basically L2 norm squared divided by D. Right. So if we do, so therefore this implies that the expectation of SZ L2 norm squared, well, that's just equal by linearity of expectation to the sum over all R from 1 to M of the expectation of SZ R squared, which we know now is m over d times L2 norm squared of z. Okay. So good. Why don't we then set pi to be something like the square root of d over m times s. That implies that the expectation of sz L2 norm squared is z L2 norm squared. Right. And now, like this pi is super duper sparse, right? I mean, if you look at the construction of the sparse Johnson-Linistrauss transform, even if you chose little s to be 1 in the SJLT, meaning every column is exactly 1 non-zero, then the total number of non-zeros in your matrix pi would be d, because there are d columns, each one has 1 non-zero, so d non-zeros in pi. This thing only has m non-zeros in pi. It only has 1 non-zero per row, not 1 non-zero per column. And the number of rows is way, way less than the number of columns. So this is even sparser than the SJLT. So that's great, right? This is really fast. I mean, how long does it take me to sample m entries? It takes me about m time, okay? So, this is like an O of m time algorithm to do the embedding. And it's giving us what we want in expectation. What's the problem? The problem is that the target dimension, the dimension that you're embedding in, is equal to the number of samples you take. And if z is a vector that's not very well spread, let's imagine, for example, z has a 1 in its first entry and zeros everywhere else, then you're going to need to take a lot of samples to even see that 1, right? In expectation, you're going to need to take d samples to see that 1, which means that m needs to be at least d, right? If you want to get any kind of concentration. So basically the problem is that yes, this is an unbiased estimator, but the variance is way too large. Not for all z, but if z happens to be sparse, then the variance is large. Okay. So Ailon and Chazel's idea was to do something to z. So you're not just going to multiply. Oh, and sorry, this should not have been an s. This should have been a pi. So Ailon and Chazel's idea was to pre-multiply z by another matrix, let's call it matrix A, such that, let's say AZ has the same norm as Z with probability 1. So A is like some kind of rotation. It's an orthogonal matrix. But it's a randomized matrix such that with very high probability, AZ is a very well-spread vector. It doesn't have all its mass in one coordinate, or even it doesn't have most of its mass concentrated in a few coordinates. The mass is kind of equally spread amongst all the coordinates for some definition of spread. If that were the case, then as we're going to see soon, you can prove that sampling works. You can get away with few samples, small m, okay? So that's the name of their game, is how do you come up with this kind of randomized preconditioner A that spreads the mass around? Okay. And I'm not a physicist, so let me not say too much because I don't actually know what I'm talking about right now, but I do know that in quantum mechanics, there is this thing called the uncertainty principle. And it's the thing that they claim also motivated them in their approach that I'm going to tell you right now. What is the uncertainty principle? Okay, so mathematically, what it says that's useful for us is a vector and its Fourier transform, let's say its discrete Fourier transform, cannot both be simultaneously concentrated in very few coordinates. If one is very concentrated in a few coordinates, then its Fourier transform has to be well spread. And the nice thing is, the discrete Fourier transform, it's a matrix, and it is an orthogonal matrix. So whatever your vector was, first apply the DFT to it. Now you have, you still have the same norm that you used to have. And if you're originally sparse, now you're well spread, and then sampling works. Okay, so that was their idea. Okay, but any guesses as to what could be wrong with that approach? If you just, let's say that I wanted, my new pi is going to be basically as, some scaling times S times the DFT matrix. So what's wrong with that? And maybe not everybody is so familiar with the Fourier transform. Let me just say one hint.
It'll be dense.
Well, what will be dense? The Fourier
transform?
The
DFT will be a large matrix, right?
That's true. The DFT itself is a large dense matrix. However, there is an algorithm called the fast Fourier transform, which says, given any vector z, I can multiply the DFT times z in like nearly linear time. So that's another nice thing about the DFT is that it has a fast algorithm. It's not just some random big matrix, it's a structured matrix, and it's structured enough that there's a very fast algorithm to multiply by it. So let me just tell you, okay, if you don't know much about the DFT, I'll just say one fact about it that kind of, using this fact alone, you can see why there's a problem. I'll just tell you that if you take the DFT of the DFT, so take Z, take its DFT, then take the DFT of that. So basically apply the square of the matrix to that. You get back the original vector. So knowing that, what's the problem?
So if Z are like the rows of the DFT matrix, then, or are the columns of the DFT matrix, then
right. So in particular,
it
like,
compresses other vectors.
Yeah. So it takes a sparse vector and spreads it out. That's great. But at the same time, it takes certain dense vectors and sparsifies them. So your original Z could have been super dense. It could have had all its mass equally spread, just as you say. It could have been a row of the DFT matrix itself. Now you apply the DFT to it, and you've ruined that spread. You've all of a sudden turned it into like the 1,0000 vector.
Isn't that true for any rotation though?
I mean, yeah. So that is true for any, but yes. So if you take any fixed rotation, then yes, something is going to have to get rotated to be 1,0000. However, this is where we introduce randomness, right? So instead of doing the DFT or some other fixed rotation, we're going to do some kind of random rotation, and we're going to do a random rotation that we still want it to be fast, but it should with high probability for any vector spread the mass around. So that's a good point, because you could just say, well, why don't I just pick a uniformly random rotation, right? You can prove that a uniformly random rotation does spread the mass around. The problem with a uniformly random rotation is that was the original JL map, right? And the problem with it is that it's slow. We don't want to use uniformly random rotation. It's too slow.
Professor?
Yeah.
So why don't we care about the fact that we're like mapping into complex numbers? Because I mean, it probably doesn't matter if it's like a complex, like it's just like twice as many data points that are storing. But like, I mean, JL lemma is stated as a map into real numbers, right?
Yeah, but if you map into complex, you can just map into real by doubling the dimension. Just like imagine if you have a plus ib, you just treat it as a two-dimensional vector, a comma b. So you can implement everything over the reals.
Okay, I see.
Also, the next thing I'm going to say is, in fact, you can avoid the DFT matrix entirely and use something that is real, like the Hadamard transform. So let me just say something. So definition. Let's say an unnormalized, bounded orthonormal system is a matrix Q such that one Q transpose Q, or let's say it should be, if it's complex, then you put a star here, I guess, which means conjugate transpose, is equal to, let's say, D times the identity. And, Q is D by D. And also, the max over all ij of Qij in magnitude is at most 1. Okay. So examples, one would be like, the unnormalized DFT. So let's say f of jk is equal to e to the minus, I guess, 2 pi I jk, or I here is square root of minus 1, just so that there's no confusion. Okay. Normally, if you want it to be orthogonal, you would have to divide by root d, but the unnormalized version, I don't divide. So this does satisfy that q star q is d times the identity. And in fact, and also all the entries are exactly 1 in magnitude. Another example is the Hadamard transform, the unnormalized, let me just write unnormalized like this, unnormalized Hadamard. So there's a recursive definition, and there's also another definition as well. But let me give you the recursive definition, which is so I can actually let me first define. So let's say here, D is equal to 2 to the R. So it's a 2 to the R by 2 to the R matrix. So when R is 0, it's a 1 by 1 matrix, and it's just the matrix 1. And when R is greater than 0, it's the matrix that looks like this. You take, let's put it here, HR minus 1, HR minus 1, HR minus 1, and then negative HR minus 1. Okay. Maybe an exercise, if you treat the indices as being 0 based, so they run from 0 up to D minus 1, then you can show that HJK is equal to minus 1 to the, I'll call it JVec dotted with KVec. So what do I mean by that? What I mean is, right, so J is a number between 0 and 2 to the R minus 1, so you can view it as an R bit number. And K is a number between 0 and 2 to the R minus 1, so you can view it as an R bit number. So now treat these R bits, treat them as actually being an R dimensional vector. Okay, so it's an R dimensional vector where each entry is either 0 or 1. And then take the dot product of these two R dimensional vectors, and it's either going to be even or odd. The dot product is either going to be even or odd. So minus 1 to an even number is 1, minus 1 to an odd number is minus 1. So HJK is equal to this. Okay, so you can prove this just via the recursive definition. Okay, prove it by induction. So these are two examples. The DFT, and both of these examples are nice in that you can multiply by them very quickly. So this you can do multiply by an O of D log D. This is the algorithm known as the fast Fourier transform. And then this Hadamard you can multiply also in D by D. And this is, let me not go through it here, but this is a very kind of simple divide and conquer algorithm. I'll let you think about that offline if you want. Okay. So good. So now this is going to be the name of the game. So the FJLT pi is going to equal 1 over square root m s h, and then I'll call this d eta, maybe. Should I call it d eta? Sure, why not? Okay, so here, this is H is any unnormalized bounded orthonormal system, like the unnormalized Hadamard or the unnormalized discrete Fourier transform. S is sampling. And then d eta is a diagonal matrix that's random. So eta 1, eta 2, up to eta d. And then 0 is on the off diagonal, where eta I is like plus minus 1. So it's uniform. It's plus 1 with probability half, minus 1 with probability half. It's what's called Rademacher random variable. Okay. And the idea is that the original Eilon-Chazelle idea was take any fixed vector, z, with high probability. So first of all, just think about what this does. What does d do when you apply it to z? It possibly changes the signs of the entries of z. So you flip the sign of each entry with 50-50 probability. Okay. If eta I is 1, you keep the sign the same. If eta I is minus 1, you change the sign. Then after you do this random sign flipping, they call it a phase transition, I think, borrowing language from physics. But after you do this random sign flipping, then you apply your bounded orthonormal system like Hadamard or discrete Fourier transform. As you're going to see from the proof, it doesn't really matter which one you do. That's going to have the property that with high probability over the choice of eta, h times d eta applied to z has very small infinity norm compared to its L2 norm. Okay, so like, imagine that it's a unit norm vector. what is the worst case? The worst case is that some entry is 1, that the L infinity norm is 1. Like all your mass, remember your L2 mass is 1. All your L2 mass is in one coordinate. The best case is like perfect spread. That means that all your entries are 1 over root d in magnitude, right? Or if we're doing the unnormalized version, remember now, this is the unnormalized h. So since it's unnormalized, it does blow up, it does blow up the L2 norm by a factor of root d. So kind of the worst case is then you have a vector, when you apply h, the worst case is there's some entry in the vector that's root d. The best case is that all the entries in the vector after you apply h are at most 1 in magnitude. You said it seems sort of related to shuffling a deck of cards. I mean, yeah, I don't know. I guess that's some discrete movement. This is some kind of rotation. But yeah, I don't. Did you want to say something?
I was just thinking earlier, potentially that a rotation could have been like a series of Givens rotations that just like corrects some coordinates. I don't know. It was just an idle thought.
Is that a Givens rotation? Does that mean 2 by 2 rotation?
Yeah. You take the 2 by 2 rotation as some submatrix.
I see. Yeah. So actually, that's a good. So I should say that the original Ilon-Chazelle paper actually suggested exactly that as a different approach, which is just let pi be the product of some number of 2 by 2 rotations. So what you're like each step, what you're going to do is you're going to pick 2 random coordinates and you're going to apply some random 2 by 2 rotation to them.
Yeah.
Then you're going to pick another 2 coordinates, apply a 2 by 2 rotation, and just do this a bunch of times. Do it like d times or d polylog d times, and then try to show that with high probability after you do this, if you then just project onto the first m coordinates, it's going to preserve the norm with high probability after scaling. So show that basically this kind of random process very quickly spreads the mass around evenly, or you don't even need that, just moves the mass to the first m coordinates.
Right. Yeah.
So they actually made that conjecture, and it was, I believe, resolved in some form. I don't know if it was a result. I don't know if the bounds they got were exactly the best one could hope for. But there was a paper by, let me see, I think Vishesh Jain, Nitesh Pillai, and at least, there were some others as well. Yeah, Vishesh, okay, so I put it in the chat. Vishesh Jain, Nitesh Pillai, Ashwin Saw, Mehtab Sawhney, and Aaron Smith. Is that?
Yeah, I actually know all those people, yeah. That's
you know them, okay. So that's the paper. And they actually analyze exactly that.
Nice.
Right. So, but yeah, so that came later. But Ilon-Chazelle just did it this way. And so let's try to understand now what, why this works.
Why don't we normalize?
Why don't we normalize?
Yeah, like is the distance supposed to like stay the same?
I mean, yeah, you could make h be normalized. If h is normalized, I mean, that doesn't really change anything. All that changes is instead of 1 over root m, you should make it root d over m. So I mean, the question is like, are you going to divide h by root d, or are you just going to divide by root d at the end? So, it doesn't really change much. So I'm just pretending that it's unnormalized, and then this root d becomes a 1.
I thought we would usually want a root.
Okay, so I mean, maybe just, I don't know if this helps the confusion. If you remember before, what I said was, I said that if you look at the expectation of root d over m s z L2 norm squared, this is equal to z L2 norm squared, right? Okay.
Okay.
We said that on the previous slide. That's basically, here.
Yeah.
So pi is this, and then I said this. Okay. So h, just the vector h itself doesn't change norms, right? H is an orthogonal matrix.
Okay, yeah, no, okay, we're good.
So, let's just say if h bar is like the normalized version, that implies that, expectation of root d over m s h bar z L2 norm squared is also z L2 norm squared. But, I can just like cancel this. I can just cancel this d with the bar.
Yeah.
Yeah, so that's all I did. Yeah.
Yeah.
Okay, so let's analyze this thing. So from now on, Z has norm 1 because, if it works for unit norm vectors, it works for every vector. So claim the probability, I think, so first let's do a reminder over here. Reminder, there's something called
Did your audio cut out?
So Jelani, your audio cut out. Yeah.
Or is this video also frozen?
I also don't think you can hear us.
His video is good for me.
Oh, his video's working.
It's frozen for me as well.
His video on his iPad is working, but his actual video is not.
I am in the iPad's still going.
Oh, I guess he heard us. Ah, it's me.
Oh, his video.
Can people hear me?
Yes.
Yeah.
Testing.
I can hear you.
Testing. Can people hear me?
I can hear you.
Okay, great.
Yes.
Sorry, I don't know what happened. My laptop just decided to boot me from Zoom, but I'm back. So reminder about Khinchin's inequality. That was from a few lectures ago. It's a tail bound for like linear forms with plus minus 1 random variables, right? This was saying that if you take x dot sigma, it decays at least as fast as x dot g, where g is a Gaussian. So what kind of decay is that? That's basically at most something like 2e to the minus lambda squared over 2 times the norm squared of x. So this is called Khinchin's inequality. So we're going to use that. So claim the probability over eta that if you look at h d eta z L infinity norm, the probability that it's bigger than something is at most delta over 2. And we'll fill in the something as we do the calculation. Let's prove it. So let's look at HD eta zi for some I. So HD eta z, the ith entry, is equal to the sum j goes from 1 to d of hij eta j zj, right? Which I can view as, I mean, maybe to be suggestive, I can view this as the sum over j of hij zj times eta j, right? So this is basically a dot product with a random sign vector. So there's one vector that has hij zj as its entries, and then the other vector has the eta is eta. Okay, so this implies that the probability that HD eta zi is bigger than lambda is less than 2e to the minus lambda squared over 2 times the norm squared of this vector, right? So what is the norm squared of this? So if you just focus on this part, that's like the sum of hij squared zj squared, right? Which, again, because all the entries of h have magnitude at most 1, this is at most z squared, which is 1, right? So that's it. So there's a times 1 here, so that doesn't matter. Okay. So good. So if I'm aiming for failure probability, so what do I want here? I want my failure probability to be less than delta over 2d, because I'm going to union bound over all I. There are d choices of I. So that tells me now how I should set lambda. If I want lambda squared over 2 to be equal to the ln of, let's say, 2d over delta, that implies that the right thing to do is to set, oh, and also don't forget that I have to kill, I should actually make this 4d because I want to kill this 2 also. So anyway, yeah, so basically set lambda to be the square root of 2 ln 4d over delta. So that's what we're going to do here. So then this becomes less than or equal to delta over 2d by that choice of lambda. So by union bound over all I, it's at most delta over 2. So this becomes square root of 2 ln 4d over delta. Questions about that? Right. Perfect well spreadness would have meant no entry is larger than 1 in magnitude. Now I'm just saying no entry is larger than roughly square root log d, which is not bad. I mean, the really bad thing would have been root d. So instead of root d, I'm root log d, which is, it's exponentially better, you can say. Okay, so now let's condition on the event. Let's define the event that this happens. Let's circle this part. Let's say E is the event that this doesn't happen. So it's the event that the L infinity norm is bounded by that, right? The L infinity norm is at most square root 2 ln 4d over delta. So the good event E happens with large probability. It happens with probability at least 1 minus delta over 2. Okay. So now we're going to just argue, okay, so now that we know E is true, let's prove that sampling works. Okay. So let's prove that. So remember now, what do we know? We know that, let's define Y to be h d eta z. And we know now that because we condition on E holding, the L infinity norm of Y is at most square root 2 ln 4d over delta. Okay. So good. What is now the L2 norm squared? So pi of z L2 norm squared is equal to 1 over m times basically sy L2 norm squared. Okay. And this is equal to, this is equal to 1 over m times, or let me write it like this. It's the sum, r goes from 1 to m, of y I sub r squared over m, where the y I sub r are IID uniform chosen from the set 1 to d. Okay. And let me just call this capital Xi. It's a random variable. It's a random variable because I sub r is a random variable. So we have a sum of independent random variables, right? We have a sum of m independent random variables. And what we'd like to prove is that they're concentrated about the expectation. The expectation is 1. It is the norm squared of z. We just need to show concentration. So theorem, I'm not going to prove the theorem in class. It's very similar to the Chernoff bound. And I give a proof in the notes that's very similar to the proof of Hansen-Wright. So if you look at the notes in the probability review section, the proof is already there. It's called Bernstein's inequality. It says, suppose you have x1 up to xm are independent, and 1, and you define also capital X to be the sum of the xi's. And 1, that for all I xi is at most k with probability 1. So it's a random variable, but it's guaranteed to be at most k. And 2, you also know that the variance of x is sigma squared. Then the probability that x minus its expectation is bigger than lambda is at most, it's at most 2e to the minus some constant times lambda squared over sigma squared plus e to the minus some constant lambda over k. So let's just take this concentration inequality as a given. I'm not going to prove it again. It's in the lecture notes. And let's see now that we can use it to directly analyze the thing above, right? The above is exactly of this form. Okay. So first of all, let's ask ourselves, what is k? Right. So k is an upper bound on any of the random variables. Remember, we're conditioning on event e here. So we know that none of the random variables is bigger than basically y L infinity norm squared, because we squared YIR, divided by m, right? And since, and then we just plug in what we know y infinity is bounded by, given that event e holds. So this is at most 2 ln 4d over delta over m. Okay. And then we know that variance of a random variable is the same thing as the expectation of x squared minus the expectation of x whole squared. Okay. Now we already know what one of these things is. This, right? Remember, this thing is an unbiased estimator of the norm of z squared, so this is 1. So when you square it, this is equal to 1. So that we know. Okay. Now, what about the other part? What about this? So let's calculate that. The expectation of x squared is the expectation of the sum over r. This should be called xr squared, which is, all of these are IID. So like the expectation of x1 squared is the same thing as the expectation of x2 squared. So this is equal to the sum over r expectation of xr squared plus the sum over r not equal to r prime expectation of xr, and they're independent, so times expectation of xr prime. But again, these two things are equal. The expectation of xr and the expectation of xr prime are the same thing. So this is equal to m, because r goes from 1 to m times the expectation of x1 squared plus m times m minus 1. That's how many ways there are to choose r not equal to r prime. Expectation of x1 whole squared. Right? People with me so far? Any questions?
Actually, why did the second term equal 1?
What expectation of x? So the expectation
Squared.
of x itself, just focus on the expectation of x.
Yes.
What is capital X? Capital X is the sum over all r of xr. Right? This is, whoops. There's no undo. Yeah, so x, this is xr. X is the sum over r of xr, which is just pi z L2 norm squared, right? So like the expectation of x is just equal to the expectation of this, which we know is equal to z squared, which is 1. So then if you square it, you still get 1.
Well, yeah.
Okay, so that's 1. So now what about the other terms that are still left? Okay. So what is the expectation of x1? Okay. So right, so the expectation of x1 is, so what are you doing? You're picking a random entry. So okay, let's just look at expectation of x1 squared. So expectation of, let's say, x1 now, we need to understand, that's this part. What is the expectation of x1? So the expectation of x1 is the sum j goes from 1 to d of the, first of all, there's a 1 over m in the definition of xr. So there's a 1 over m. Probability that that you sample that let's say JR, or sorry, I guess I should call it a 1R, that you sample J times yj squared. Does that make sense? And the probability you sample J is 1 over D, right? So this is equal to 1 over dm, 1 over md y squared, y L2 norm squared. What is the L2 norm squared of y? Well, remember, y is basically, you first of all, you applied d eta to z. That doesn't change the norm. Now you applied h to that. H is an unnormalized orthogonal matrix, which means that it blows up the norm by root d, which means it blows up the squared norm by d. So the norm squared of y is d times the norm squared of z, which means those d's cancel, and what you're left with is 1 over m. 1 over m times the norm squared of z, which is 1. So that's 1 over m. Okay. And then I guess the last part I'll do over here. So what's the expectation of x1 squared? So it's basically the same thing as before, except instead of yj squared, it's going to be yj to the 4th, because you square it, right? It's x1 squared. So this is equal to, and there's also 1 over m squared. So this is equal to 1 over m squared times, again, you're going to pick up a 1 over d, times the sum over j of yj to the 4th. Now, yj to the 4th is equal to yj squared times yj squared. Okay, I'm not saying a whole lot here. Yj squared times yj squared. Well, I know that yj squared is at most y infinity squared, right? So, so this is at most. So again, and I can replace. So okay, so I'll just do this. So this is at most 1 over m squared d times, again, my 2 ln 4d over delta.
Where did the d in the denominator come from?
Oh, it's the same d as this d. It's the same reason as this d. Oops. Remember there was a d over here? It's the same d as this d. It comes from this.
Oh, yeah.
So the only thing that's different now is because I'm doing x1 squared and not x1, instead of having that yj squared there, I have a yj to the 4th. But everything else is the same. So I still have 1 over md, but now I multiply by the sum of yj to the 4th instead of the sum of yj squared. And then yj to the 4th, I'm just saying, is at most yj squared times yj squared. But yj squared is at most this, because we're conditioning on e. And then what I'm left with is the sum of yj squared. But just like before, the sum of yj squared is d. So that d, so then I also have the sum of yj squared, but that cancels with this d. Okay? So I know there's a lot of math on here. Let's go to a clean board. So basically, summary. k is at most 2 ln 4d over delta over m. And then sigma squared we said was at most, so there's a -1 because there's this -1, there's this minus, remember that right here, right? There's this -1 over here. So there's a -1 plus, we have m times the expectation of x1 squared plus m times m minus 1 times this thing. So let's just plug all that stuff in. So there's basically a +1 plus m times m minus 1 times 1 over m times, and actually that should be 1 over m squared, times 2 ln 4d over delta. Does that make sense? Okay. Questions?
Wait, on the previous slide,
Yep.
wait, where did the extra sum over y squared come from? They canceled with the d?
Are you talking about for the right-hand side of the board or the left-hand side of the board?
Bottom right.
Bottom right. So
We have the orange sum over yi squared.
the sum over j of yj to the fourth?
No, below that and to the right. Like you see.
So I just said, yeah, so maybe I'll have to put it here. Maybe I just said that the sum of yj to the fourth is at most, the sum of yj squared. It's equal to the sum of yj squared, right? Which is at most y infinity squared times the sum of yj squared. And this I have a bound on because I'm conditioning on event E.
Yeah.
And
I just
this,
replaced one of them.
this I know is equal to D. Right? Because y is just an unnormalized orthogonal matrix multiplied by Z.
Yeah.
So it blows up the norm by root D. It blows up the squared norm by D. Okay.
And then that ended up getting plugged into this thing on this slide.
Yeah. So overall, this thing is at most 2 ln 4d over delta. I can't help but feel like I lost a factor of m somewhere. That's okay. So this implies all by Bernstein that the probability over eta and, well, the probability over pi really, which includes both the randomness from S as well as the randomness from eta, that, okay, so actually, well, let me do it like this. So let me just randomness over S. Pi h d eta z L2 norm squared minus 1, the probability that's bigger than epsilon, conditioned on event E, is at most 2 times e to the minus epsilon squared over so good. So this thing is, that's why I'm almost certain I lost a factor of m. Let me just be a little careful here. Just look and see if I can spot why I lost my factor of m.
Did you get both of those terms though? Right, like,
Both of which terms?
well, you have the expected value of x squared, and you have the first one, which is the same. Did you not multiply that by m?
You're saying here?
like on the bottom right, when you compute the expected value of x1 squared, right, that should be multiplied by m because there's x1, x2 up to.
I don't.
Cool.
Well, so x1 squared is equal to 1 over m squared times y-ir to the fourth for some r.
Yeah, but then once you compute that, right, like we were computing that because we had that in the above sum with sum r equals 1 to m of expected value of xr squared.
But I think I'm taking that into account because I have, that's why I have an extra factor here of m times n minus 1. Right? That's because of this, that came from this.
Yeah, well
That's because I was already summing over r here, right?
yeah, or what about the term to the left of that one? On the diagonal.
This part?
Yeah. Like you found the value of one of those terms, but then you should multiply by m.
Yeah, so that was this, right? That gave me 1 over m, but I multiplied by m. That's why I have a +1 here. That's why I have this +1. That's from the diagonal terms. And then this is from the off-diagonal terms. Okay, so let me just write this out and then maybe I'll send an email afterward if I don't see it immediately, but even in the notes, I think I have this, do I have the same typo? Possibly. Aha. Yeah, I'll fix that later. Oh, yes. I think I know what's wrong, finally. I think I completely forgot that there's a square here. Right? There's a square right here. I basically multiplied the wrong thing by the wrong thing. So this okay, sorry. This is my fault for trying to cram too much into one whiteboard. But basically, right, this 1 over m right here. Can people see what I'm circling? Let me use a different color. This 1 over m that I'm circling at the bottom of the middle of the screen right here, that came from the expectation of x1, right? Which is exactly this expectation of x1 over here all the way on the right-hand side. Okay, so I need to take that and square it and then multiply that by m times m minus 1. So that's the red thing that got circled there. So now I'm feeling a little bit more confident. So that part there is plus m times m minus 1 over m squared. And then this other part here, that's the thing that's this is actually the diagonal. So that part in red, that is this part, the diagonal right here, right? So you take the expectation of x1 squared, which is what we calculated, and you multiply that by m, right? That's this bottom right part. So that gives you 2 times the ln of 4d over delta over m. Okay? So now I think we're in business. So now this is going to be 2e to the minus. So now we apply Bernstein, we get 2e to the minus c epsilon squared over sigma squared. So you divide by sigma squared, which means you multiply by m over 2 ln 4d over delta. And then the other term in Bernstein is e to the minus c epsilon. And then now here you have k. You divide by k. What is k? K is m, or if you divide by k, it means you multiply by m divided by 2 ln 4d over delta. So this is less than delta over 2 for m, which is large enough, namely m, which is at least some constant times 1 over epsilon squared, log 1 over delta, times log d over delta. And that implies that the probability over pi of that you succeed, meaning that the norm is preserved, that's certainly at least the probability of event E times the probability that you succeed given event E. And what we've shown is that's at least, well, the probability of E is at least 1 minus delta over 2. The probability that you succeed given E is also at least 1 minus delta over 2, which is more than 1 minus delta. And that's what we wanted. So I think now that's it. I'm sorry for the little calculation confusion for a second there. But again, I know this was a lot of calculation, and you know, it is already in the notes. I've already uploaded this to the notes online. But any questions before I show you the next kind of analysis that I wanted to show you due to Kramer and Ward? Oh, and there's actually one more thing I wanted to say too, which is if you remember for DJL, distributional JL, I don't want to map to dimension 1 over epsilon squared. I don't want to map to this dimension. This has an extra factor of log D over delta, right? The optimal thing is M should be 1 over epsilon squared times log of 1 over delta. That's it. This has an extra factor of log D over delta. Okay, but I'm going to address that right now after questions. So before I address how to improve that part, which is going to be a very simple thing, any questions about anything that you've seen so far? Right, so the highest level is, oh yeah, Noah, you unmuted.
I was just saying the calculation, the problem with the calculation before was just that you switched the diagonal and off diagonal.
Yeah, I confused myself between what was diagonal and what was off diagonal. One of them had an M squared, one of them had an M. Since I swapped that around, I lost an M that I really needed to make things work out. But once I unswapped it, then everything was saved. Okay, so how do you fix the fact that M is not perfect? So M is now this, up to a constant 1 over epsilon squared log 1 over delta times log of D over delta. So here's, and that's my matrix pi, right? So that's my, let's call this M prime. So my matrix pi has M prime rows. So what I'm going to do is I'm going to just map down to slightly less rows. So now this has M prime columns and M rows. This is my pi prime. And let's call this pi double prime. Pi double prime is what we just analyzed. And M is going to be 1 over epsilon squared log 1 over delta times some constant. I'm just going to set pi to be pi prime times pi double prime, where pi prime has, IID plus minus 1 over root M entries. Does that make sense? So pi prime is a dense random matrix, the same as like the original JLs that people were doing that was slow. But the point is, I started at dimension D. I got down to almost what I want. I got down to M prime. But now I can, it's more affordable now to apply a slow matrix because I'm not applying it to a huge vector. I'm applying it to a tinier vector. It's only M prime dimensional. So the total time is something like, well, the time it takes to apply pi prime is D log D, mainly dominated by the fast Fourier transform or the fast Hadamard transform, right? And then now I need to apply pi prime, and that takes time, basically M prime times M. And, that's roughly, it's at most up to a log D factor like M cubed or something. Right, up to the log D. I mean, the point is, if you ignore the epsilons for a second, it's a little better than that. But if you ignore the epsilons for a second and ignore the D, M prime is like log squared 1 over delta, and M is like log 1 over delta. So M prime times M is like log cubed 1 over delta, right? Which is like M cubed. So you're getting running time, which is D log D plus M cubed. So as roughly, ignoring the log D. So the point is, as long as, as long as m is less than cube root of d. So as long as you're doing some like serious dimensionality reduction here, then the m cubed term is dominated by the d log d term anyway, so you don't mind. But you could imagine that if I'm just trying to map from a d dimensional vector to a root d dimensional vector, then this could be a killer, because root d cubed is like d to the 1.5. So my runtime is not great. Does that make sense? So anyway, that's what iLearnHL got. And they did it slightly differently than what I'm saying. In particular, they said rather than do pi prime times pi double prime, and this pi double prime is exactly equal to 1 over root m times s times h times d eta. And this is equal to some slow JL. So what the original AC paper did was they actually replaced S. And they said, rather than make S a sampling matrix, let's make S like just very ultra sparse, but it's not quite a sampling matrix. So a sampling matrix has one non-zero per row. Essentially what they did is they said, okay, why don't we just make each row of S have like log number of non-zeros? Or I mean, specifically what they did was they said, we're going to pick a distribution where like each entry of S is going to be 0 with very high probability. Otherwise, it's going to be a random sign. But the probability that it's not 0, the probability that it's a random sign is like very, very, very small. So kind of an expectation, you only expect like log or polylog non-zeros per row. So it's almost as sparse as a sampling matrix, a little bit denser. But by doing that, they were able to, then they didn't have to apply the pi prime at the end. They could just kind of analyze the whole thing in one go and get a very slightly better bound too. But it was still something like d log d plus m cubed. Okay, so that was the original AC paper, AC06 paper. Questions about this? And then if not, I want to say something about the Kramer-Ward, which I'll be able to get through probably a decent chunk of it, but I won't be able to finish the analysis probably today. We'll do that on Monday. So questions about anything here? Okay. So the KW analysis just kind of thinks about the problem just very differently. So so we had a matrix which looked like pi, which is 1 over root m SHD. So, and actually I should say that the original AC, iLearnHL paper, they called their ultra sparse matrix P instead of S. So it was PhD, and it was I think one of the main results in iLearn's PhD thesis. So anyway, just a little bit of trivia. So the AC paper, basically the argument is that with high probability, HDZ is nice, meaning well spread, so sampling works. The KW analysis kind of looks at it differently. It puts the parentheses somewhere else. It says with high probability, S, 1 over root m, SH is nice. So putting in the D gives JL. Okay. So they kind of parenthesize things in a different way, and they show that if you do that, you can actually get some bounds which are nicer than the AC bound, which are better. And it was very surprising because, what is the definition of nice here? So the definition of nice for AC06 was that the vector is well spread, the mass is well spread. The definition of nice for the matrix SH for KW is that it satisfies something called the restricted isometry property, which has to do with compression and compressed sensing, which we knew as a community, as a research community, we knew that if you had a JL matrix, you could use it to come up with RIP matrices. That was kind of a standard thing and not that hard to prove. You'll see that later in the course. But I think no one ever even expected that the opposite was true. If you have an arbitrary RIP matrix, restricted isometry property, that somehow implies you can cook up a JL matrix out of it by putting in this D. Okay, so what is this RIP, this restricted isometry property? So this is RIP. So definition, Let's say pi satisfies the, let's call it epsilon comma k restricted isometry property, if for all k-sparse vector z, we have that pi preserves its norm. Okay. So it's like, I mean, JL is, when we talk about JL, it's on a finite point set. Here, this is an infinite point set, right? This is the set of all k-sparse vectors. Okay, so meaning that the number of non-zero entries in Z is at most k. So this is a completely deterministic property. There's no randomness in this definition, right? You can talk, like it's sensible to talk about a fixed matrix. Does this fixed matrix have the RIP or does it not have the RIP? Okay, so for the identity matrix, yes, the identity matrix has the RIP where k can be as big as you want and epsilon can be 0 because it preserves the norm of every vector, not just sparse vectors. But it turns out that you can come up with other non-trivial matrices that also have the RIP that have the number of rows that depends only on k. And kind of a theorem, and this is due to, originally due to Candace and Tao. Later, there's an improvement by Rudelson and Verschinen. Later, there's an improvement by Haviv and Regev, or there's one by Bourgain, John Bourgain. There's another improvement, all technical improvements, the same thing by Haviv and Regev. But the bottom line is that with high probability, 1 over root m sh satisfies it satisfies epsilon comma k RIP as long as m is at least something like k times log d times, I want to say the best bounds might be something like log cubed k. So polylog k. I can't remember if it's log squared k or log cubed k. Okay. So that's that. So we know, and we might get a chance. It uses some ideas from probability it uses this technique of chaining and Dudley's inequality. I'm not sure we're going to get a chance to cover this in the course. I'll see whether we have time. But it uses some nice ideas. But let's just take it as a given that this matrix SH satisfies RIP with good probability, and the number of rows, other than up to these log factors, the number of rows just depends linearly on k. So now let me state the Kramer-Ward theorem. Kramer and Ward. Suppose that pi satisfies epsilon comma 2k RIP for k being some constant times log 1 over delta. Then we get DJL. Then for all z of unit norm, the probability over eta that if you look at pi d eta applied to z L2 norm squared, let me call it sigma now. Sigma is a random sign vector. Minus 1 is bigger than epsilon is at most delta. So that's their theorem. So pi can be a deterministic matrix, right? RIP is a completely deterministic property. So once pi satisfies this deterministic property for a large enough sparsity, k is the sparsity that it has to preserve norms of, then once you throw a d sigma into it, remember d sigma is like you take a diagonal matrix, you put random signs in the diagonal, sigma 1, sigma 2 down in the diagonal, then you get DJL. Somehow randomly flipping signs of a vector, applying an RIP matrix gives you DJL. That's the theorem. Questions about the statement of the theorem? Okay. So let me try to start the proof. I think I'll get far enough along that I can at least define all the relevant things that go into the proof, and I can basically outline what you do. But then I might not have time to actually do the calculations. So I'll basically set it up so that kind of next time in the beginning of lecture we can do those calculations. They won't be too painful, and then we can move on. Okay, so let's see, how do you prove this? So kind of the first observation is that, like, what is d sigma z? It's a vector. And it's a vector that looks like this. Sigma 1 z1, sigma 2 z2, etc. Sigma d zd. And this is of course the same thing as dz sigma. Right? Meaning you put the entries of z on the diagonal. So that implies that pi d sigma z L2 norm squared, right? That, what is that equal to? That's equal to pi dz sigma L2 norm squared, which is equal to sigma transpose dz pi transpose pi dz sigma. And I can write this as sigma transpose basically capital X sigma, where like X is some matrix. And this is a quadratic form. So as you might imagine, we could hope to use something like Hansen-Wright to say that it's concentrated about its mean. Okay. So let me try to better understand this matrix X. Okay. So what I said was we're interested in bounding. So we want to bound the probability that sigma transpose dz pi transpose pi dz sigma minus 1 is bigger than epsilon. And I call this matrix X. I call this matrix capital X. So let's try to understand what capital X looks like. Before I do that, let me permute the coordinates. So without loss of generality, assume that like X, not X, Z is the vector. Z1 is bigger than or equal to Z2, is bigger than or equal to Z3, etc. So let me just rearrange, all the arguments that I'm giving are not really sensitive to the labeling of the coordinates. So just permute the coordinates around so that when I say coordinate 1, I actually mean the coordinate corresponding to the largest entry of Z in magnitude. Coordinate 2 corresponds to the second largest entry of Z, etc. So, whatever permutation that I'm doing to the entries of Z, I'll similarly permute the entries of sigma. I'll similarly permute the columns of pi so that I haven't really changed anything. Okay. And then now what I'm going to do is I'm going to define like Z. So Z is this vector, which is d-dimensional. I'm going to look at the top k entries, the next k entries, the next k entries, etc. And so this has size k. And I'm going to call this vector, I should have written this a little wider. This vector, I'm going to call it Z1, I guess. Okay. Actually, let me do it like, so that I don't get confused with subscripts and superscripts. So this is Z1, This is Z2. This is Z3, etc. And similarly, if I look at pi is some matrix. It has D columns and some number of rows. And what I'm going to do is I'm going to look at the first K columns, the next K columns. So this has K columns here, this has K columns here. And I'm going to call this pi 1, and I'm going to call this pi 2, etc. Okay. So I'm just permuting entries and columns to be consistent with this rearranging of Z. And then what I'm going to do is I'm going to look at this matrix capital X that I was talking about up above. It's some matrix. It's a square matrix. And I guess this matrix is D by D. And what I'm going to do is I'm going to look at the diagonal entries. Oops, sorry. I'm going to write these blocks along the diagonal. So this goes down the diagonal. And these are each K by K. And I'm going to call, A is basically, when I say A, what I mean is the matrix which only has the diagonal blocks kept, and the rest of the matrix is gone. The rest of the matrix got zeroed out. So that's what A means. And then B is going to be this matrix. So this matrix here is B transpose. And then everything else that's left in the matrix, I'll just call C. Okay? Does that make sense?
What got zeroed out with A?
So, okay, so I guess what I mean is, so X kind of looks like this. X is the square matrix. And then I kind of partitioned it into these blocks, right? I did this to X, I mean. And then I did this, and then I did this. And then I guess what I'm saying is, like, let me color this now. There's the red parts. There's the yellow parts. Let's say that yellow part. And then there's the, I guess, light bluish part. Oh, wait, that's not what I wanted. So what I'm trying to say is that A is basically this matrix. That's A. B is this matrix. That's B, right? Which means that this right here is B transpose, basically. And C is, what you expect now. C is, if you again draw that picture. So C has a 0 here, 0 here, 0 here, 0 is all down the diagonal, and then it only keeps these entries. Does that make sense? I guess wrong color, but you know what I mean. So I decomposed, so basically what I'm saying is, like, at the end of the day, X is equal to A plus B transpose plus C. I just partitioned the entries in this way. Okay. And then, so now what I need to do is I need to understand. So now what I'm going to do is I'm basically going to say, or what KW did was they said, well, sigma transpose X sigma is equal to sigma transpose A sigma plus sigma transpose B sigma plus sigma transpose B transpose sigma plus sigma transpose C sigma, right? And what they said was like, this is 1 plus or minus epsilon. And this, they didn't use any randomness whatsoever. They just used RIP. This is also like O of epsilon. And for this, they're going to use Kinchin. This is the same thing, basically. So it's O of epsilon, Kinchin. And then this, they're also going to prove is O of epsilon. And that's going to be via Hansen, right? So I only have 4 minutes left. So I think what I'm going to do is, let me do one of them. Let me show you that the first term is 1 plus or minus epsilon, which, by the way, if you remember, at the end of the day, we're looking at sigma transpose X sigma minus 1, right? So when you subtract at 1, that's basically going to cancel this one. So overall, you have like plus or minus epsilon 4 times. So this whole thing is like roughly epsilon, some constant times epsilon. And then you get the bound. And I should say, so, okay, good. So this is 1 plus or minus epsilon with probability 1, if given that you have RIP. And this is with high probability, this is with high probability, this is with high probability. Namely like 1 minus delta, basically. So let's do the first one, sigma transpose A sigma, because I think that's the easiest one. And then we can take a break until Monday. So sigma transpose A sigma is equal to sigma, basically, I did superscripts before, but I'm gonna switch back to subscripts because otherwise it's gonna get in the way of the transpose. So this is like sigma 1, meaning you just keep the top k entries of sigma, the first k entries of sigma. Okay, well, actually, if you want me to be more, let's do it like this. This is equal to sigma transpose, and then it's something like d z1 pi 1 transpose pi dz1 sigma. So this might as well be sigma 1 transpose and sigma 1. And this is a 1 also. Okay. So good. Oh, no, sorry. This is not just 1. Yeah, this is, we're going down the diagonal. We're going down all the diagonal blocks. So this is really like the sum over all blocks. I goes from 1 to, how many blocks are there? D over K, because there are D coordinates, each one, there are K blocks, each block has size K, and there are D coordinates, so there are D over K blocks. So I'm summing up over all the blocks, and I'm looking at, basically sigma transpose times that block sigma. So this is sigma, the ith block, ith block, ith block. So these are all sub i's. And then this is equal to the sum over I of, again, remember, we said this earlier, like d eta times x is the same thing as like dx times eta. So I can use that to say this is zi transpose d sigma I pi I transpose pi I d sigma I zi. And this is equal to the sum over I of pi I d sigma I zi L2 norm squared, right? Remember now, A L2 norm squared is just like A transpose A, which is exactly what you're seeing here, right? This is basically my A. So this is A transpose A. So that's the L2 norm squared. Now, what do I know about this vector? What do I know about this vector d sigma I zi? It's k sparse, right? Zi is the ith block of z, which only has k coordinates in it. Each block only has k coordinates. So zi is a k sparse vector. When I apply d sigma I to it, I'm just changing the signs. It's still a k sparse vector. So pi preserves its norm because pi is RIP. It preserves the norm of any k-sparse vector. So this is equal to 1 plus or minus epsilon times the sum over I of d sigma I zi squared. What's the norm of zi after I apply d sigma to it? It doesn't change at all. D sigma just changes signs. Changing signs doesn't change the norm. So this is the same thing as 1 plus minus epsilon times the sum over I of zi L2 norm squared. But of course, this is the same thing as 1 plus or minus epsilon times the norm of z squared, which is 1 plus or minus epsilon, right? Because all I'm doing is I'm looking at block by block, what's the contribution to the L2 norm squared per block, summed over all the blocks, that gives me everything. That gives me all of z.
So pi being like k epsilon RIP implies pi I is as well.
Yeah, so I mean, just observe that pi times any vector b is like the same thing as pi restricted to the support of b times b. Does that make sense?
Yeah.
Meaning that just keep the columns of pi that correspond to the support of b. So I mean, pi, I mean, I guess what I'm saying is that pi I times zi is the same thing as pi times zi. There's no difference.
Oh, where zi is still like full d-dimensional. You just zeroed out the rest.
Yeah, exactly. Does that make sense?
Yeah.
Yeah. So
this is probably a minor point, but if this is only players where we use RP, why do we need it to be with 2K?
because it's not the only place we use RIP.
Ah, I see.
Sorry.
Okay.
So I should say,
Thanks.
yeah, so all of these are like, it's like RIP plus Kinchin, RIP plus Hansen Wright. So this is this right here that I've circled is the only inequality here, right? Everything else was just equality. This is the only place where I said, look, there's some approximation because there's some inequality because this thing is RIP, but everything else was equality. Okay, so that's it. It was completely deterministic. I didn't use any randomness of anything here. On Monday, we'll see how to handle the other remaining terms. And for that, we actually will use randomness. And we will, again, use RIP. So yes, that does. So I hope that answers your question. This is not the only place we're going to use RIP. So that's all I have for today.